Welcome back to the machine learning lecture. This week, we continue our discussion on dimensionality reduction and matrix factorization techniques. In this video, we will focus on matrix factorization, which is a technique which has many applications, out of which the most popular one is in recommender systems. You're probably interacting with recommender systems on a daily basis. Whether this is a system which recommends which movie you should watch next, as in on Netflix, or which song you should listen to next, as in on Spotify, or maybe which product you're interested in, or you might be interested in. And the way these systems work is they first of all look at the overall behavior, so what kinds of users enjoy what kinds of movies or songs, but they also look at your personal behavior, what kind of movies you've enjoyed in the past. And based on this data, the system comes up with a list of movies or songs which you're likely to be interested in, and then presents this list of movies or songs to you. And in this video, we're going to learn about one way to build such a recommender system. Before we dive into the details, in order to provide a little bit more motivation, I want to discuss the Netflix prize competition. So in 2019, Netflix organized a competition in which they invited anyone to participate. And the whole goal of this competition was to build a system, a recommender system, which outperforms their internal recommender system. And they provided data, training data to the participants, which was in the form of a set of users, a set of movies, and the ratings. Specifically, they gave a data set which had almost 500,000 users and a little bit over 15,000 movies. And this data set, the way it looked like is basically, it had a list of tuples in which it said user 1 gave a rating of 1 to the first movie. The second user gave a rating of 3 to the second movie. The second user gave a rating of 5 to the third movie. So the way you can think about it, and the way this is illustrated on the slide, is that we have a huge matrix with 500,000 rows and 15 million columns, and each of the cells in this matrix tells us the rating that a certain user gave to a certain movie. And overall, Netflix provided 100 million ratings, which means that this matrix had 100 million entries in it. The first thing here you should notice is that this matrix has missing entries. And if you kind of think of how many potential cells are into 500,000 by 15,000 matrix, 100 million is a very small fraction of these ratings. So there's lots of missing entries in this matrix. Okay, and the way it divided the training data and test data, basically it looked at the ratings in a period of 6 years, and then the ratings during some last time period were saved as a test data. The score, which was used to kind of evaluate the different recommender systems people would submit, is the root mean square error. So we're going to see on the next slide exactly how this is defined, but basically you take the actual rating and you calculate the difference to the predicted rating. And just to note that the internal system that Netflix was using had a root mean square error of 0.95. And also just another side note is if you kind of do the most trivial thing, the basic thing you can imagine, where you kind of predict the average rating. So you take all of the ratings, compute the average, and predict this number for any potential users, you would get a root mean square error of 0.54. So this is the trivial solution. And we see there's roughly a 10% improvement. So they only managed to do a 10% improvement over the trivial solution, even though they tried very likely really hard to do better. So in order to incentivize people to compete, they decided to offer a prize of $1 million for any team which can achieve at least 10% improvement over their internal score of 0.95. So this kind of tells you that it's a difficult problem, and also it's a problem worth solving, because having better recommendations means that more people are going to use your service. Okay, so now let's briefly talk about more how these systems are evaluated. So as I said before, the data is in terms of a set of tuples, UI, where each tuple is related to a given user U, which have rated a certain movie I or a certain item I. So here you'll notice I'm using the terms movies and items interchangeably, because this system doesn't have to be necessarily about movies. It could be also about songs, about products, or something else. Okay, so we have for each user that have rated an item I, the actual rating RUI, which can be between 1 and 5, for example. So a rating of 1, 2, 3, 4, or 5. And the way we evaluate this system is based on the root mean square error, which basically just takes the true rating minus the predicted rating, which is based on some system, which we're going to see how this looks like. We take the difference, square it, sum it all over all possible items in our set, and take the square root. So pretty simple. And systems which of course have lower RMSE are likely to lead to better recommendations. So one thing here I want to point out is how the training and test data look like. So basically, if you go back to the previous slide, you can imagine that this is the data set that you were given by Netflix, and what you're going to do is you're going to randomly select some of the ratings, put them in the training set, and then the remaining will be put in the test set. So some of these squares were randomly put in the training set, they are shown in blue, and some of the other squares are randomly put in the test set, and these we'll use these to evaluate our system. So what you also notice here is we have lots of white cells, and these are the missing data. So this is exactly the goal which the recommender system is trying to accomplish, right? So let's say we look at the first user. The first user has watched the first 3 movies, and it has given them a rating of 1, 3, and 4. And in reality, we would like to predict what are the ratings for the remaining movies. So let's say that we have some system which predicts that the user will give a rating of 2, 1, and 5. And once we've predicted the potential rating for all of the movies in our data set, we simply pick the top K. So in this case, let's say we pick the first one, which will be this movie, because we predict that this user will give a very high rating to this movie. So this is what we're going to recommend. Right, so basically you're going to use the blue cells to train your model, you're going to use the green cells to evaluate your model, and then once you've built and trained your model in production, you're going to use the model to predict the white cells, right? Okay, and then I also want to make here a distinction before regression and between regression and recommendation, because if you look at the metric, it looks very similar to what we would do in a regression setting. So we're predicting a scalar number, right? I also want to make here comparison with regression or supervised learning tasks, which you've seen before, and recommendation. So basically in regression, we're given a data set, let's say with users. So each row is a user. For each user, we have a set of features, and then we're trying to predict a single variable. Maybe this is the likelihood that the user will buy a house. And the way we're dividing the training and test data is basically we select a bunch of rows randomly, we use these to train the model, then we held out another set of rows which we use to evaluate our model. But then once we've built and trained the model, then new users come in with their own features, and then we're trying to predict the single label, so the single variable. right? So basically we have, let's say, d-dimensional input features and a single dimensional output label, which we're trying to predict. And this is slightly different in the recommendation task, where now the training and test data is kind of scattered all over this matrix. And instead of trying to predict a single label, basically we're trying to predict the rating that the user is going to give to all of the other movies that the user has not seen yet. So this task also is sometimes called a matrix completion task. Because in some sense, what we're trying to do is trying to find the best way to complete all of these missing entries in our matrix. Right, so let me just annotate a couple of more things here. So this is what you use to build your model. And then in production, you're predicting the labels for the new incoming users. While in the recommendation settings, you're using these cells to build your model. And then the white cells you use in production. Okay, and then I'll just repeat it one more time for clarity. Once you've completed this matrix, once you've, for example, predicted that this user will give ratings of 2, 3, and 4 to these movies, the way you actually do recommendation is you take the top K movies, and this is the movies that you show to the user. One potential way to solve this problem is using a tool which we've already discussed in one of the previous videos, and this is the singular value decomposition. So what we're going to do is we're going to take the rating matrix. So this was the matrix where each row is a user and each column is an item, and we're going to fill in all of the missing data with zeros. So everywhere where we didn't know the rating that the user gave to the item, where we had an empty or a missing cell, we're going to plug in a 0. And then once we have this matrix R, we're going to run the singular value decomposition on this matrix in order to recover, let's say, K latent factors. So the way the singular value decomposition looked like, if you remember, basically we decompose any given matrix into 3 terms, U, sigma, and V transposed, and then we're only going to keep the K terms, the K factors, which correspond to the K largest singular values. So just again, for reminder, if we have any matrix, we can decompose it into U, which is a unitary matrix, sigma, which is a diagonal matrix, and V transposed, which is also a unitary matrix. And then once we've found this decomposition, we're only going to keep the entries corresponding to the top K largest singular values. Right, here we also do one additional just piece of notation where we have taken U and sigma and we've collapsed them together into a single factor, which we call Q, and we've also simply renamed the V into P. So this is then P transposed. So the way you can think about this, what this does is, given a matrix of ratings with zeros filled in, we've decomposed it into 2 other matrices, Q and P transposed, where the Q matrix is a user to factor matrix or a user to concept matrix. We gave this example in the SVD video, where each of these factors corresponds to some latent movie concepts. And similarly, the P transpose matrix is an items to factors matrix. Okay, so why does this make sense? Why would we do SVD? Well, for one thing, we already know that the SVD gives us the minimal reconstruction error in terms of the Frobenius norm, right? So we know that the minimum over all possible matrices B, where the rank of B is equal to K between R and B in terms of the Frobenius norm, is exactly given by the U sigma and V transposed, right? So we know that we can construct a low rank matrix K by taking the K first singular values and K first left and right singular vectors, put them into the matrix B, and this will give us the optimal reconstruction error in terms of Frobenius norm. And the Frobenius norm is nothing else but the sum of squared errors, right? So all of the terms in R minus all the terms in the reconstruction of R squared and summed up. And if you now look at the sum of squared errors, we see that the root mean squared error is just monotonically related to the sum of squared errors. So it has an additional normalization where it divides by the total number of entries. So instead of taking the sum, we're taking the mean, and it also has the square root. So basically, SVD already is minimizing the root mean square error because it is minimizing the sum of squared errors, right? So this seems perfect, right? Great news. The RMSE was our metric, and SVD is directly minimizing our metric. It's directly minimizing our error. However, it's not ideal because in order to get to this point, we had to take the matrix and fill it in with zeros whenever we had missing data. And if you think about what this semantically means, you already realize that it's not a good idea, because zero rating means that the user didn't like the movie, right? But zero rating is not equal to no rating. So the user, if we go back to the matrix, so we actually don't know how this user would rate this item, right? Maybe this user would have really liked this item and given it a high rating of 5, but what we've done is we've plugged in a 0. And if you think about what SVD is doing, SVD is trying to reconstruct all of these entries in the matrix as best as possible. So if there's a high number in the original matrix, SVD is going to try and get a high number in the reconstructed matrix. If there's a low number in the original matrix, SVD will try and get a low number in the reconstructed matrix. And then what this means is that SVD will try to reconstruct all of the zeros in addition to trying to reconstruct all of the actual ratings that we've observed. And this is not ideal because no rating is not the same as zero rating. And in general, SVD is not a good technique for this kind of task because it cannot handle missing data. It's not built to handle missing data. In addition to this, we also do not really care about the orthogonality and normalization constraints which are imposed by the SVD solution. So if you remember, we know that U transposed is the identity and V transposed is also the identity. So the U and V matrices are orthogonal, but we don't really care about this, right? The only thing we care about is getting a low RMSE, so a low reconstruction error, and imposing these constraints might just be a hindrance. So we rather solve this problem unconstrained. So to summarize, even though SVD gives us the optimal low-rank approximation in terms of the Frobenius norm and is at the same time minimizing the RMSE, we don't really want to use it because it cannot handle missing elements. So these are elements which we have not observed, and treating them as 0, which means a very low rating, is not ideal. And in general, we often have this problem of two kinds of zeros, where a 0 can either mean that we have not observed that, or it could also mean that it's actually a rating of 0. And treating these kinds of zeros appropriately is very difficult if you don't know where the 0 comes from. Okay, and then yet another issue which SVD has is that the factors that it produces are dense. So the top case singular vectors, left and right singular vectors, are dense vectors in the sense that there's not that many 0 entries in these factors, right? But this seems counterintuitive because intuitively, in order to generate sparse-looking data, likely the underlying factors are also sparse. And in addition, if we have these dense factors, they might be more difficult to interpret. You can imagine you have just a, I don't know, n by k matrix of a bunch of numbers. This is much more difficult to interpret than if you have a sparse n by k matrix with only a few non-zero entries in here. Okay, so because of all of these issues with SVD, we're going to put it aside, and we're going to try again in order to solve the recommendation system problem. Specifically, what we're going to look at is what are called latent factor models. So now our goal is again to find two matrices, Q and P, just as before, where the interpretation of Q and P is the same as before, that it's Q is a user times factor matrix, and P transposed is an items times factor matrix. But this time, we're not going to impose any constraints on Q and P, and we're simply going to minimize the sum of square errors. But here comes the crucial detail, which is different from SVD. Instead of minimizing over all possible entries, so let me go back one more time to the SVD. So here SVD minimizes over all UI, so over all entries in the matrix, including the zeros that we plugged in. Now, when we are solving this optimization problem, we're only going to minimize over the observed entries. So we're only going to look at the error over these blue squares in the R matrix. Okay, and how can we solve this problem? Well, as it turns out, we're going to be able to use some standard optimization techniques. And just for some piece of notation here, so that everyone is on the same page, the RUI is a scalar number. So this is the rating that user U gave to item I. QU is a row vector, and it's the row of the matrix Q. So QU is a row vector of size 1 by k, and PI is also a row vector, also of size 1 by k. So when we do QI dot, sorry, let me write that again. So when we do QU dot PI transpose, this is a 1 times k times k times 1, because it's 1 times k transposed for PI, and this is 1 times 1, a scalar. Right, so the way you can think about this is that each user has its own latent factor. So each user has some k-dimensional vector, k-dimensional latent vector, and also each item has its own k-dimensional latent vector. So each item has some latent embedding, also called sometimes. And to do prediction for user U and item I, basically we take the latent factor of the user, QU, we take the latent factor of the item, PI, take the dot product, and this gives us a scalar. So this is then the prediction for user U and item I. Right, so now we have the setup. The thing that we have to do now is solve this optimization problem and minimize the error with respect to P and Q. So how are we going to do this? This seems like a difficult problem because the variables here are interplaying with each other. And you cannot really directly solve it by taking the gradient and setting it to 0 or something like that. Well, one approach which does work in this scenario is the so-called alternating optimization approach. Sometimes this is also called block coordinate minimization. And simply what you do is you start with some initial values for P and Q. We'll see how we get those. And then you alternate between keeping P fixed and solving for Q, and then keeping Q fixed and solving for P. And as we're going to see, making this alternation scheme is going to greatly reduce the complexity of solving the underlying problem. So in pseudocode, how this looks like, again, we initialize P 0, Q0 at the 0th iteration, and then in each iteration, we first keep Q as a fixed. So we pretend that Q is a constant, and now solve the problem with respect to P. So we only minimize the error with respect to P. And then we do it the other way around, where now we say we're going to pretend that the latest version of P is constant, and we're going to solve the problem only with respect to Q. And we're going to keep alternating between these two steps until we converge. And the way we know that we've converged is maybe the error is not going down anymore, or the actual P and Q values that we're learning are not changing by much. Okay, so another way to think about this, just as a side note, essentially, why this thing is called block coordinate minimization. So you can imagine that you have two variables called P and Q. So now these variables are a single dimensional variable, but you can imagine the same thing holds in general for matrices P and Q. And let's say we have some error function, which is here denoted with these contour lines, and this alternating optimization, starting from some initial point PQ, first goes into one direction, then goes into the other direction, then into the previous, and so on, and keeps alternating into between solving for P and solving for Q until it reaches the minimum. In other words, we have two coordinates, P and Q, and first we keep one coordinate fixed and we solve for the other one, then we keep the other one fixed and solve for the first one, alternating until we converge. In general, this is called block coordinate minimization because you can think of the Q matrix as a block of coordinates together, and of the P matrix also as a block of coordinates together. Okay, so this is the picture you should have in mind, what I've drawn on the slide. And the overall algorithm is you initialize and you alternate until you converge. So now let's dig into the details of how we do each of these steps. First is the initialization. And one thing here which is sensible is to use the solution of the singular value decomposition. So what we've talked about on the previous slides. What we can do again, take the rating matrix, plug in zeros, solve the SVD, and use the P and Q factors from the SVD. Alternatively, we can also, instead of plugging in zeros, we can plug in the overall mean, or the row-wise or column-wise mean, or some other heuristic. Sometimes what works better, instead of starting with the SVD, is to use just random initialization, where you randomly sample the entries, let's say, from a normal distribution. Next, we discuss how to solve these alternating optimization problems. For the moment, let's assume that we're at some iteration t, and we assume that Q is fixed, and we're trying to solve for P. And if we write this out, so it's the same optimization problem as before. We're summing over all of the entries that we've observed, and we're taking the sum of squared differences. But now, instead of treating QU as a variable, we're treating QU as a constant. And we're only optimizing with respect to P. And the first observation, which is critical here, is that because Q is fixed, this problem can be solved for each of the PI vectors independently. We can decompose it from this one big problem into the smaller problems. And in order to see this, know that we can take this sum and rewrite it per item. So this big sum can be written as sum of all of the U1 terms in S. So all of the users which have rated the first item are U1 minus QU P1 transposed squared, plus then all of the users which have rated the second item are U2 minus QU P2 transposed squared, plus so on and on. Right? And then in each of these terms, now QU is a constant, RU1 is a constant, and the only variable in these terms are the P1s, P2s, P3s, and so on. And because there is no other variables within these sums, essentially, these terms, we can solve for each of them independently. Because if we minimize this term plus the next term independently, the whole sum will also be minimized. And this is what's written here. So essentially, the equation, the minimization problem on the left, is equivalent to solving d independent optimization problems, one for each item. And the notation we're going to use here is this set S star I, which simply denotes all of the users which have rated that item I. Right. And equivalently, the same thing holds the other way around. If now P is fixed and we're solving for Q, we're going to get the same thing, but now we're going to have optimization problems over QU, and the sets that we're going to be working with is the sets of U star, or the sets of all users, sets of all items which have been rated by a particular user. The second observation is that each of these mini problems with respect to PI is just a simple regression problem, which I hope you already know how to solve, because we've discussed this in one of the first lectures in this course. So let's briefly recap what a simple regression problem is. We're given a set of instances, in this case n instances, and each of the instances has a feature vector xj, so this could be, let's say, a d-dimensional vector, and a scalar label or a scalar regression target yj. And what we're trying to do is we're trying to fit a linear model where the prediction is simply w transposed xj, where w is the vector over which we're optimizing over. The cost function that we're computing here is similar to the recommendation setting, and it's just the sum of squared errors. Okay, so this was the optimization problem of linear regression. We know how to solve this. This is a convex objective function, so we can simply take the gradient with respect to the parameters w, set it to 0, and solve. If we do this, we can obtain the optimal solution for w in closed form, and this is shown here on the slides. This might look a little bit strange to you because here it's written out in terms of sums, but this term is equivalent to x transpose x inverse x transpose y, where x was this matrix where we've stacked each of the features of our instances, and y was this vector where we've plugged in all of the regression targets. Right, so this here is a d times d matrix because, so be careful, xj and w are column vectors, which means xj is a d times 1 column vector multiplied with d times 1 transpose, which is 1 times d. So this is, as I said, a d times d matrix, which is then inverted. So w, computing the optimal w in matrix notation is the same as computing it in this sum notation. Okay, but this problem and this problem now looks very similar. So our RUIs are YJs, our QUs are XJs, because these are the constants, and our PI transposes are W transposes. Be careful here, the Q and P are row vectors, and XJ and W are column vectors, which just means we have to put in the transpose in the correct place, but otherwise these two match. If we do pattern matching, we see that they're similar. Okay, so now let's then take this form of the optimal solution and now plug in Q and P where appropriate. So we see instead of having 1 over n, we have 1 over the total number of users which have rated this particular item. Then we have QU transposed instead of this term, and then we have QU transposed RUI. Okay, so apparently solving this problem is just a simple regression problem, and then we can find the optimal PI transposed for each of the i's directly in closed form. And then if you do the same thing for QU, it's again true. Now just the order is switched. Now QU is the variable and PI is the fixed constant. We were able to reduce one step of the alternating optimization procedure to solving simple linear regression problems. Again, keep in mind the big picture. We started with an objective which was where we were optimizing over both P and Q. Then we said we're going to do alternating optimization steps where we only optimize over P and only optimize over Q. And now we saw that solving this problem equals to solving many small linear regression problems. In general, alternating optimization can be a very powerful technique because it allows us to take a complicated, potentially non-convex objective function and decompose it into smaller optimization problems which we know how to solve. In our case, these were simple regression problems which are very efficient to solve. And overall, this algorithm can be easily implemented, and it's just a few lines in Python. I think you're going to see this because this is part of one of the homeworks. The other thing I want to point out is that the solution here, or the algorithm, is very efficient because these sets of only the users which have rated item I, or only the items which have been rated by user U, are also very small. So if you think back to the big rating matrix, which was 0.5 million times 20k, this is a huge matrix. But if you look at, let's say, one particular user U, this user has only rated a handful of items. And then when you're solving each of these individual regression problems, the number of items equals the number of instances. And this is very small, so solving, computing these matrices and finding the optimal solution is also very fast. Okay, so alternating optimization has some benefits, but it also has some drawbacks. And the first thing is that it only gives us an approximate solution. So this step of decomposing, solving with respect to P only and with respect to Q only will not be guaranteed to find a global optimal solution. And in general, it may get stuck into a local optimum. But moreover, the bigger issue with alternating optimization is that it's highly dependent on the initial solution, so the initial P0 and Q0 that you use. One way you can kind of counteract this is by taking many different random initializations, running alternating optimization on all of them, and then simply taking the one which gives you the best error or the smallest error. This algorithm for solving the matrix factorization problem is only one option that we have. Another option is to simply do gradient descent. Depending on the data, either of these two approaches might give you better performance. So let's briefly recap how we do gradient descent. Well, we simply define an objective function denoted with L, and in our case, the objective function is just the sum of squared errors. Then we take the gradient with respect to each of the parameters and then step into the negative direction of the gradient in order to update the parameters. And step size is determined by the learning rate. So in this case, we have some learning rate eta, and we step into the direction of the negative direction of the gradient with the step size eta. If we're looking at stochastic gradient descent with a batch size of 1 as a simple example, then the gradient updates actually simplify by a lot. So in this case, we see the gradient update for QU is a simple function of this helper variable EUI, and the same thing holds for the gradient update to PI. And this helper variable, you can view it as the current error, how much we're off with the current prediction from the target prediction. So this was for a batch size of 1, where we take a random user U, a random item I, we look at the rating RUI, and then we simply compute the gradient for that particular QU and that particular QI. If you have a larger batch size where you have multiple ratings, again, the gradient update is pretty simple. You just sum up all the terms that contribute to U and all the terms that contribute to PI. Okay, now that we know how to learn Q and P, either with the alternating optimization or with the gradient descent approach, or in other words, that now that we know how to obtain the latent factors QU for each user and the latent factors PI for each item, the question is, how do we do prediction? Well, it's pretty simple. We just take the dot product between the appropriate user vector and the appropriate item vector. Let's work through one numerical example, and let's say we're trying to find the prediction for the rating that the user 2 will give to the item number 5. Well, we simply take the second row of Q, because this is the factor corresponding to the second user, and the fifth column of P transpose, because this is the factor that corresponds to the fifth item, take the dot product, and we see that in this case it evaluates to 2, 4. Now, this allows us to do rating prediction for each individual user item pair, which means that we can just go through this matrix and fill in all of the missing values. So that's why this approach is sometimes called matrix completion, as I mentioned earlier. And once we have all of the values, how are we going to predict, how are we going to recommend some items? Let's say we know that for this user, we're going to predict 3, 2, 1, 4, 2, 3, 5, 5. As I said earlier, we're simply going to take all of the items or the top k items which have highest predicted score. And in this case, let's say we do the top 3, which will be this one, and this one. Now, basically, you have all of the building blocks you need in order to build a simple recommender system. And indeed, if you look at the recommender system, which won the Netflix competition challenge, you'll see that they use matrix factorization, so what we've learned so far, as one building block. And in addition to this matrix factorization approach, they throw in a couple of other ideas in order to push the performance further. And some of those other ideas involve modeling global effects and something else which is called collaborative filtering, but we're not going to go into the details on these. I do want to mention something about these global effects, and they come into play because different users tend to have essentially different baselines of what they consider good or not good. So you can think of that, for example, certain users are overly pessimistic and they always give ratings which are pretty high, like 4s and 5s and 4s and 5s, while other users tend to be pessimistic and only give very low ratings, between 2 and 3, and very occasionally give a high rating of 5. And something similar might happen with the movies or with the items, where certain items are very popular and always get a high score, while other items are very unpopular and always get a low rating. And in order to kind of capture these effects, what we can do is we can simply introduce additional bias terms which will account for these effects. And basically that's what we do. So we take each user and add one additional variable, BU, so this is a scalar, which captures the bias of that user, and something similar for each item, we add one additional scalar variable, BI. And on top of this, we can add one more global bias, which kind of holds for all of the users and all of the items. And if we look at the new optimization problem, basically it looks exactly the same as before, but now we've added these new terms, BU, BI, for each user and each item, and the additional global bias, and these are also now part of the minimization, so we are optimizing over them. Okay, so one more thing here I want to mention is the so-called cold start problem. So you can imagine if I have a recommendation system and I've built it and works pretty well, what happens now if a new movie comes into my system? Because nobody has seen this movie yet, nobody has given it a rating, so I cannot really predict which users are going to like it. One thing you can do here as a potential solution is to kind of randomly choose users, show this movie to those users, and get an initial set of ratings, and based on those ratings, estimate how other users are going to like or dislike this movie. When it comes to the users, you can also have a cold start problem where when a new user joins the system, because we don't have any history of how this user rates movies, we can't really predict which movies this user is going to like or dislike. Here it's more difficult to solve. What you can do is you can use some additional data. So if you know some demographics data about this user, maybe you can match it to other users who have similar demographics data and then predict the movies that those users with similar demographics also enjoy. And then again, once you have enough ratings for that user, the issue will go away. Next, I want to discuss two important aspects of matrix factorization: how to deal with overfitting and how to induce sparsity in the learned latent factors. Remember, what we're trying to do is get good recommendations, which means we want to achieve low test error on unseen test data. But because we don't have access to unseen test data, we instead minimize the error on the training data. In the matrix factorization model, one of the key hyperparameters is the number of latent factors k, or in other words, the dimension of the q, u, and pi vectors. And you can probably already imagine what's going to happen as we change this number. Let me illustrate this. So let's say our x-axis is the number of latent factors k, and our y-axis is the error. And normally, naturally, as we're increasing the number of latent factors k, the train error will keep going down and down. And that's because we have more free parameters, we have more freedom to capture all of the variation in the training data. Let me annotate this as the train error. But as you can already guess, for the test error, this is not the case. First, the test error decreases, and at some point, the test error starts increasing. This is essentially a form of overfitting, because we have too many free parameters. In addition to capturing all of the signal in the training data, we also capture all of the noise. And even though we have excellent performance, so low error on the training data set, we start having high error on the test data set, which means we're not generalizing. We have overfitted to the training data. And in particular, in the case of matrix factorization, this issue could be even worse than normal. And in order to think about this, think about the number of data points that we use to estimate each of the small regression problems. So again, we were solving many small regression problems where the number of parameters we're estimating is k, so is equal to the latent size, and the number of actual data points equals to the number of ratings that a particular user has made, or the number of ratings that a particular item has gotten. So these two sets. And depending on the user or the item, these two sets can be quite small, and in particular much smaller than the number of latent factors. And when this happens, the linear regression solution will overfit, and in some cases this might even lead to an undetermined system of equations, which means that the problem is ill-posed. Okay, so overfitting is an issue, and you already know how to solve it, right? We've discussed this many times before. The simplest solution is to just add regularization. And regularization simply penalizes the length or the norm of the vector. The idea, again, just to remind you, is that if we don't have any other information, the length of the vector should be small, the norm should be small, because then essentially it has small effect on the outcome. And if you also remember back to our discussion in the linear regression slides, adding regularization corresponds to putting a certain prior on the weights, where L2 regularization corresponded to putting a prior with a normal distribution, and L1 regularization corresponds to a prior with a Laplace distribution. In our case, adding regularization amounts to adding these two simple terms to the objective function. We go over all users u, and we penalize the norm of the latent factor qu. Same for all items I, we penalize the norm of the latent factor pi. We introduce two additional hyperparameters, lambda1 and lambda2, which trade off how much do we care about having small norm, small length, versus how much do we care about having small error, meaning good reconstruction. Let's visualize what the effect of regularization is on these latent factors. And for example, let's focus on the item factors or the movie factors. So here I show two-dimensional movie factors, which means that if R was our rating matrix, then we had, this was approximated with Q and P transpose matrices, where Q was an n times 2 matrix and P transpose is a 2 times D matrix. In other words, for each of our movies, we have a two-dimensional vector which represents the latent vector for these movies. And now we can take these latent two-dimensional vectors, plot them, and see what is going on and how these change as we change the regularization strength. So first, one thing that's interesting, if we learn Q and P transposed, we're going to see some interesting semantic meaning that is captured in these latent factors. For example, we see that the first factor captures the amount of action, in this case, in the movies. We see that as we go to the right, these movies have more action, and then as we go to the left, these movies have less action. And similarly, the second factor, which is shown on the y-axis, seems to capture somehow semantically the movies which are more funny versus the movies which are more serious. So more serious as we go up and more funny as we go down. Now, what we're going to think about is what happens to the latent factor of one particular movie. So let's say this movie, which is shown here with the icon. And we're trying to reason about what happens as we increase the regularization strength, meaning now we increase the lambda hyperparameter and we see what happens as we learn Q and P transposed. Well, because lambda penalizes the norm, and you can think of the norm as this length from the latent vector to the origin. As we increase the lambda, we should expect that the length gets smaller and smaller. And this is indeed what happens. So as we increase the regularization, the latent factor for this movie gets closer and closer to the center. This makes sense not only from the point of view of overfitting, which we've discussed in previous lectures, right? So having smaller length means we have smaller influence on the prediction, but also it makes semantically here sense, because the closer we are to the middle, the more we are undetermined, right? We are more, we're not sure if the movie is serious or funny, or has less action or more action. Now, if the movie has very few ratings, then out of the two terms, the error term will be not as dominant, and the regularization term will be more dominant, which means it will pull the movie close to the center, which means that this movie is undetermined, so to speak. On the other hand, if the movie has many ratings, the error term will dominate, and the regularization term will not be as strong, which means the movie will be free to be, for example, over here or over here, so be more determined in some sense. Okay, let's see how the regularization now plays out when we plug it in to the alternating optimization procedure, which we discussed in the previous slides. Here again, I repeat how the regularized problem looks like. We have the same thing from before, plus these two additional terms. Now, again, we can solve these small regression problems where we're solving for the parameters of each pi and each qu independently. And we see basically this looks like a ridge regression now. The same thing as before, plus we have this L2 penalty on the norm of the parameters pi. And you know how to solve this, right? So we have just a closed form solution. You can look at the linear regression slides, but just for a reminder, the way this looks like, the solution will be something like x transposed x inverse x transposed plus lambda I inverse x transposed y, where we now have this additional term which comes from the regularization. And as I've just discussed, having larger lambda forces the parameters to be smaller and smaller, which in turn avoids that we capture a lot of noise. Okay, so yeah, in the case of alternating least squares, the problem doesn't change much. Instead of solving a normal regression problem, we solve a ridge regression problem. In the case of gradient descent, it's again pretty simple. Now, if we now let's say we assume again that we do stochastic gradient descent with a batch size of 1. So we pick one random user and one random item, and we look at the gradient with respect to the parameters. The gradient update equations look exactly the same, but we have these two additional parameters which come from the regularization terms. Here also, by the way, I've included the bias terms, BU, BI, and B, and we see that these also have pretty simple gradient updates, as we see here. So you can also implement them in a rather straightforward manner. Now we know how to handle overfitting. We simply add regularization terms to the objective function. Turns out we can also handle sparsity using the same regularization terms. But we have to be careful about which norm we use. If we use the L2 norm, which is the default choice, the solution will not be sparse. If we instead use the L1 norm, we'll tend to get solutions in which most of the parameters are close to 0. That is, we'll get a sparse solution. And this is a general phenomenon. Whenever we use the L2 regularization term in an objective function, we'll get solutions which are not sparse because most of the parameters are shrunk equally in all directions. If we instead use the L1 penalty, the L1 regularization term, we allow some of the values in the parameter vector to be quite high, and then we compensate by setting other values close to 0. In general, as we've discussed previously, sparsity is desirable. For one, it makes the results more interpretable. If you think about a long vector, it's easier to interpret what this vector means if most of the values are close to 0 and only few values are non-zero. And in addition to this, sparse vectors require less memory to store, and then processing with sparse vector is also faster. Okay, now let's see and try to build some intuition of why does L1 promote sparsity in comparison to the L2. Okay, so here on the slide I show a constraint optimization problem where we're minimizing some function f of the weight vector w subject to the norm of that weight vector be less than equal to 1, for example. So we're minimizing over w. And in this example, w is two-dimensional, and we're trying to think about what happens when we have the 2 norm versus the 1 norm in the constraint. So here, just to make things clear, this constraint optimization problem is only for illustration purposes. In the matrix factorization problem and in this lecture so far, we have been only working with unconstrained optimization problem. And to see the connection between this constraint problem and an unconstrained problem, note that if you take the dual of this constraint problem, you'll get something like f of w plus lambda, the norm of w minus 1. So then you already see the connection between this constraint optimization problem and this unconstrained optimization problem. But because it's easier to think about what happens in the constraint optimization problem and it's easier to build intuition, that's why we're going to work with this version. Okay, so back to the optimization problem. We see in the illustration the objective function, which is shown with these contours. And then we also see the constraints, that the parameters, so the parameter w vector is two-dimensional. It has two components, w1 and w2, and we're enforcing that the norm of the parameters is 1. And this is encoded with these two shaded regions. So this part is where W2 is less than 1, and this part is where WL1 norm is less than 1. Okay, and this, as I said, these contours show us the objective function, and because we're trying to minimize, we're trying to get as close to this point as possible. So in general, if we did not have a constraint optimization problem, this would be the minimum in both cases. But now, because we have a constraint optimization problem, we're looking for the point within this shaded region which is as close as possible to the minimum. And in this case versus this case, we see that the solution is slightly different. Now let's look at an animation of how the solution changes as we're changing our objective function. We see that the solution, or in other words, the closest point within the shaded region to the minimum, can be different in the L2 versus the L1 case. And this is shown with this orange dot over here. So this orange dot is the closest point to the minimum that still satisfies the constraint that the norm, in this case the L2 norm, should be less than 1, and in this case the L1 norm should be less than 1. And we see that for many different versions of the objective function, which are shown now with this rotating contour line, so for different versions of the rotating contour line, we basically have different objective functions. So for many versions of the objective function, the solution is often at one of these corners. So here we say it's at one of these corners, then it shifts to the upper corner, then it stays there for quite some time, then it shifts down to the other corner. And basically all of these corners are sparse solutions, because at this corner we have a W1 of 1 and a W2 of 0. And at this corner it's the other way around. We have a W1 of 0 and W2 of 1. While if we look at the other solution, so for the L2 regularization or for L2 penalty, we see that almost never we're at these points which give you a sparse solution. So in most of the cases we are somewhere in between, which means we get a non-sparse solution. To summarize, adding regularization helps to both prevent overfitting and it promotes sparsity if we use the L1 norm. Now, for the final part of the video, I want to briefly talk about some extensions of matrix factorization. In general, matrix factorization is a very powerful approach. You can use it for dimensionality reduction if you directly use the QU and PI low-dimensional factors. You can also use it for visualization to better understand your data. Simply compute 2D or 3-dimensional latent factors and plot them and try to observe any hidden structure. We did something similar a couple of slides ago, where we showed the latent 2D movie factors, and we saw that they capture some sort of semantic meaning. We saw that on the x-axis, the movies were aligned according to the amount of action, and on the y-axis, the movies were aligned according to whether they were more serious or more funny. We also saw that one of the main applications of matrix factorization is to predict missing values. And this was the running example where we were trying to predict the missing ratings of users and items. Using this, then we could build a recommender system. Because matrix factorization is so popular and powerful, many different extensions have been proposed. And these extensions often focus on trying to handle different types of data, trying to enforce different constraints, and one of the main goals in these extensions is often to improve the interpretability. One such extension is the Boolean matrix factorization approach, where we're trying to factor a Boolean matrix, so a matrix with only 0 or 1 entries, into Boolean factors. So the latent factors also have to have only 0 or 1 entries. And such matrices often come up when we have, for example, social networks, where we encode in the matrix whether user I is friend with user J. Then the cell ij in the matrix will have a value 1, and if they're not friends, we'll have a value of 0. A similar type of extension is called non-negative matrix factorization. And this is useful because often data is given in form of negative values. And if you think, for example, even the ratings that we discussed so far, those are non-negative because they're between 1 and 5. Income, age, different kind of counts are non-negative. The number of words in a document, grayscale images, all of these different kinds of data have non-negative values. But if you do SVD, or even the matrix factorization approach that we discussed so far, in the learned latent factors, you will also get negative values. But this is a little bit counterintuitive because we can assume that positive values are only generated from positive factors. So then one thing we can do is to directly try and learn only positive factors. And non-negative matrix factorization exactly does this. So the way we frame this is that we want to factorize a non-negative matrix A into non-negative Q and P in order to have a good reconstruction error. And this can be framed as a constraint optimization problem, and then we can use tools similar to what we've learned, for example, in the support vector machines lecture to solve such constraint optimization problems. And just to show you how this looks like, in this case we have face data, so data of grayscale images, which is again non-negative, and you can imagine that this data is stacked into a matrix, something like this, where then each of these rows is one of these faces flattened. So what you can do is you can train a normal model, such as PCA or SVD, and train a non-negative matrix factorization model. And then we see that the non-negative matrix factorization model, because it has only 0 and 1 values, seems like it's more interpretable. Okay, so that was for this video. We've discussed matrix factorization, and we discussed especially how you can use this approach for recommender systems. In the next videos, we discuss other non-linear dimensionality reduction techniques, specifically neighborhood graph methods and autoencoders. Thank you for your attention.